Hello and welcome to this video on finding a basis for the null space of a matrix. So in this video, I'm going to define what the null space of a matrix is, which I've done also in a previous video, if you've been following. Also, I'm going to define what does it mean for a set of vectors to be a basis for a vector space. Right, because you'll see that the null space of a matrix is a vector space, satisfies all 10 vector space axioms. In fact, it's a subspace of some Euclidean space, Rn, R2, R3, and so on. Then after that, those definition pages, I'm going to be going over several examples where I'm given a matrix, and then I'm asked to find the null space of that matrix, and then find a basis for the null space of that matrix, right? So the title of the video. Okay, so let's begin. So this first page, again, if you saw my last video where I introduced this page may look familiar. I'm using the exact same one. The null space of a matrix. Right. So if A is an m by n matrix, right? So m rows, n columns, then the set of all solutions of the homogeneous system of linear equations, so you take the matrix A times some column vector x, right, some variable matrix if you want to think of that. When's that equal to the zero vector, right? Just a bunch of zeros. Remember, this was called a homogeneous equation or homogeneous system, where you had all your equations with variables and stuff over here, variable terms, and then zeros all on the other side. So the solutions are these vectors x. When I talk about all the solutions, I'm talking about vectors I can replace x with to make this a true statement. And the set of all these solutions is a subspace of Rn, right? Rn called the null space of A, right? Denoted as null space of A, nulla, right? Null of A. Now in this little orange box down here, you can think of the null, so the null space of a matrix, the null space of A is all the vectors belonging to Rn, all the vectors x, such that the matrix times those vectors is equal to the zero vector, right? Again, all the solutions of this equation, Ax equals 0. Now I did underline that, this set here, this null space of a matrix, is a subspace of Rn, right? Meaning all the vectors are in Rn, and it too is a vector space. Remember, to show some subset of a vector space was itself a vector space, you need to show that it was non-empty. So that's what I've got over here. Again, I wrote this up last time, a little tiny. Sorry. Obviously the zero vector's in here, right? Any matrix times the zero vector would in Rn would give me the zero vector in Rm. So the null space is non-empty, and it's closed under vector addition, right? If a vector x and a vector y were in this space, that means A times x equals the zero vector, A times y equals the zero vector, and there should be an arrow above that, right? A vector, zero vector. Then their sum, x plus y, would also, when you multiply it by a, give me the zero vector, because you can distribute. That's ax plus ay, or 0 plus 0. You'd get the zero vector back with x plus y as well. So if x and y are in the null space, so is x plus y, and it's closed, and therefore it's closed under vector addition. And then if x is in, if some vector is in the null space, then any scalar multiple of that vector will also be in the null space. And you can check out my little line down here. A times Rx, where R is a scalar, will be equal to the zero vector as well. So it's closed under scalar multiplication, right? And of course I'm defining vector addition and scalar multiplication here with the standard operations, right? The way you're accustomed to adding vectors and multiplying vectors by scalars. Yeah, if I ever come across examples with non-standard operations, those will of course be defined for you. Alright. Alright, so now the next page, another definition you've probably seen. I've had this page up on previous videos of mine as well. What does it mean for a set of vectors to be a basis of a vector space? Alright, so a set of vectors from V, right, some vector space V. Say this set of vectors is called S, with vectors v1, v2, up to vn. There are n vectors in S. This set of vectors is a basis for V if the following two things hold. If S spans V, or in other words, V equals the span of S. I remember what the span of a set of vectors was. This was just the set of all linear combinations of the vectors in S, right? So this is saying that every vector in the vector space can be written as a linear combination of these n vectors. Right? Also, the set S is linearly independent. That means that every vector in here cannot be written as a linear combination of the other vectors in S. Or the more clearly defined way of stating that, this equation here, if you took a linear combination of the vectors in S, say x1 v1 plus x2 v2 plus xn vn, where x1 x2 all the way up to xn are scalars, and say when is that equal to the zero vector, if only the trivial solution is a solution, right? If only zeros for all the if all the values of x's have to be 0 to make this true, and that's it. That's the only way that you can make it true. Then the set of vectors is linearly independent. All right. So when you think of a basis for a vector space, a set of vectors as a basis, think of these as like the building blocks for V. Right. S spans V means I can build any vector I want from V with just these n vectors, right? Take a linear combination of these n vectors and build any vector from V I wish. And the fact that they're linearly independent means that I need all of them, right? None of these depend on any of the others, so all of them are necessary building blocks. All right, you might have also heard this referred to as therefore a minimal spanning set for V. Right? It's a set that spans V with as few vectors as possible, as few blocks as possible. Okay. All right. So now we have the definition of null space out there, definition of basis out there. Let's go into my examples. All right. So for the rest of the video, I'll be given a matrix, called A. And what I'm going to be asked to do is find the null space of the matrix, right, this null space of A. Then find a basis for the null space of A, right, a basis for that vector space called the null space of A. Alright, so remember what we're doing. If you watch my last video on finding the null space, this is kind of a repeat of that. The only thing that's being added is, finding this basis, and it's not that much more. But what we're trying to do here is, find solutions to this equation. A times some column vector x equals the 0 vector. All right, now look at the matrix I'm given here. This is a 2 by 3 matrix, right? 2 rows, 3 columns. So if A is a 2 by 3, that means that these vectors, this x needs to have 3 rows. It needs to be a 3 by 1. So x would have to look like this, x1, x2, and x3 have 3 components, right? Be a 3 by 1 column vector. And then this final result, right, the 0 vector would be if I take the 2 by 3 times a 3 by 1, I'm getting a 2 by 1. Right, it's going to be the 2 by 1 0 vector, right, the vector from R2. Okay, so then we're looking at solving this. So I'll replace the a and the x and all this. All right, so let's go over here. So again, bear with me. Like you've seen me in other videos. Again, if you've been watching, I like to, for the first maybe 1 or 2 examples, show you all the long way, right, a long way around doing things, and then we'll skip to some shortcuts for the last several examples. So here's matrix A multiplied by these vectors x, right? And we want to find all the values of x1, x2, and x3, all these vectors x, such that this is equal to the 0 vector, right? Which is again the 0 vector in R2, a 2 by 1. And as you've seen probably, I'm assuming, if you've been working on stuff before this, right? If you're seeing null space now, there's a good chance you've seen systems of linear equations before. When you have a matrix equation like this, right, this corresponds to a system of linear equations, and it would be the following system. So if I perform the matrix multiplication here, a 2 by 3 times a 3 by 1 would be this left side would give me a 2 by 1, where the first component would be 1x1 plus 5x2 and then plus 8x3. And in order for this side to be equal to this side, that first component needs to be equal to 0. And then the second component would be negative x1 and minus 6x2 and then plus 1x3. And again, in order for this to be true, this would need to be equal to 0. Alright, so I get this system of linear equations involving x1, x2, and x3 here. And then, as with any system of linear equations, right, there's a corresponding, the way I like to solve them is write the corresponding augmented matrix. So as an augmented matrix, sorry, this says augmented, right, where down the first column, write the coefficients of x1, so 1, negative 1. Down the second column, the coefficients of x2, 5, and negative 6. Third column, coefficients of x3, pardon me, 8 and 1, little bar where the equals are going. And then the other side, the constants, right, 0 and 0. And what you're going to notice in the future examples is I'm not going to write this column of zeros over here because, when I go and I'm going to perform row operations to put this matrix into reduced echelon form or reduced row echelon form. So, when you perform row operations, any column that's full of zeros, that's all zeros, is going to remain that way. So in the future examples, I'm just not going to write this and write the coefficient matrix. Now look at the coefficient matrix. See, the coefficient matrix is simply matrix A. Alright, so I'll just recopy matrix A down, and really all I'm going to focus on is putting matrix A into reduced echelon form in future examples. Alright, so now I'm going to do that here. Now this only has a couple rows, so I can do this one by hand if I have a calculator ready, but I'll be using that more often in the future examples. So I'm going to put this into reduced row echelon form, RREF. Again, this time I will write the zeros, right? This column of zeros won't change. Now if you look at again, I'll do it by hand here for this first one because there's only a couple rows. The first row, the first non-zero entry is a 1, which is what I want. So there's a pivot entry, and then everything above and below that I want to be 0. Well, there's nothing above it. So I would just simply add these two rows together to get a new second row. So 1 plus negative 1, right, that would give me the 0 that I wish for down there. 5 plus negative 6 would give me negative 1. 8 plus 1 would give me 9, right? And then again, 0 plus 0, no biggie, right? Then I would, looking at the second row now, I'm done with the first row's pivot position. The second row has a pivot position, right? The first non-zero entry is here, right, at -1. And then I would like, zeros above and below that, and I'll turn that into a 1 as well after we're done. I would just simply multiply this by 5 and then add it to that, right, to make this into 0. Get zeros above the pivot as well as below, but there's nothing below. And do the same thing here. Multiply this by 5, which is 45, plus 8, 53. All right, and that's it for the row operation. Then again, 0 times 5 plus 0, 0. Again, these always stay zeros, the columns. And then I would multiply this row by -1, making this +1 like I wish, right? Having the first non-zero entry be a 1, where this pivot entry be a 1. And this by -1, making that -9, right? So in reduced row echelon form, I got 1, 0, 0, 1, 53, -9, and then the zeros, right? Now, remember, these each column represented the coefficients of certain variables, and you looked for, your pivots. The first, these leading ones in the rows. So this first row has this, leading one, this pivot position in the first column. So x1, right? This column is a pivot column. x1 is what they call a basic variable. The second row, the leading one down here, the pivot position is in column 2, so x2 is also basic. Right? So these two are basic, meaning they're going to be fixed values once I've chosen the values for my free variables, which is what this column corresponds to. At this column, the third column, has no pivots in it. So the variable x3 is free, meaning I can replace x3 with any real number I wish, and once I do that, then x1 and x2 will be able to be found. You can't just replace x3 with anything you want and then x1 and x2 with anything you want either, right? It might not be a solution. Alright, so as I like to do with free variables, you can keep the free variables the way they look. You can keep this as x3 if you wish, but I like replacing the free variables with some other parameter, some other letter, or some other expression that can take on any real number value. Usually it's just a letter T for me, right? T or S or R. So I'm going to replace x3 with T, where T can be any of the real numbers, right? T belongs to the reals. Alright, so then looking at the first row, looking at this first row here, taking this over here, first row tells me that x1 plus, no x2, and then plus 53x3, or 53t. So plus 53t should be equal to 0. So the value of x1 in any solution is going to be -53 times my choice of t, right? My choice of the free variable. Then the second row has x2, then -9x3 or -9t equals 0. And solving for x2 there, x2 would then be 9 times my choice of t. And now we have a description. We have every variable written in terms of this free variable I called t. Now we can describe all the solutions. Right? So the solutions of this equation here, this matrix A times this x vector equals a 0 vector. All the solutions look like this. You have vector x. Again, looks like this. You have x1, x2, x3. But there's a certain form they take, right? Like I said, x1 is -53 multiplied by this choice of t. x2 is 9 times the choice of t. And x3 is whatever I choose for t. Right? And if you look at this, right, every single, now there's only one free variable, right? And every single value in any solution depends on the value of the free variable t. They all have t as a common factor, so I could pull that scalar out, right? Remember scalar multiplication for vectors, you can pull scalars out if it's common to all components. So I pull t out, and this is times the vector negative 53, 9, 1, right? The coefficients of t. All right, so what we're seeing here is that every solution of this equation, what we are seeing right here, is that every solution of this ax equals 0 equation that we're finding is a scalar multiple of the vector negative 53, 9, 1. Now in that case, you could say it's a linear combination of this vector, but when you have a linear combination of one vector, that's just a scalar multiple. Is a scalar multiple of the vector negative 53, 9, 1. Right, that from R3 there. Great. So remember, and this is the null space then. All right. Remember, the null space is all these solutions, right? All these solutions to ax equals 0. All right. So I can describe the null space in a couple ways. All right. So the null space of A, the null space of that matrix A is equal to, and then I just write the descriptions, just like I did, just right here. T is all the vectors that look like this. Some number t times the vector negative 53, 9, 1, such that t is real, is a scalar. I could write it that way, or this is the set of all linear combinations of this one vector, all scalar multiples of this one vector. So that is also, you could write the span of that single vector. Right? The span of the set with just that vector negative 53, 9, and 1 in it. Right? So either way is fine. I prefer the span way because I think it's a little shorter to write. But both are equivalent. All right? They mean the same thing. This set, saying the span of this vector and saying this all scalar multiples of this vector. They are the same thing. All right, and if you've done everything proper, and if you would like, you can check, take scalar multiples of this, take 0 times this, which would be 0, 0, 0. Again, that's the obvious solution to this equation. But replace t with any number you want. T with 1, you have negative 53, 9, and 1. Plug it in, see if you get something that's true. T with 2, t with 100, t with 5, t with negative 7, t with a third, pi, square root of 2, whatever real number you wish to replace t with. You can do that and then check to see if it's a solution, and it should be. Okay, so now for the basis part. If you've done everything like I've shown you up till now, where you put the matrix A into reduced echelon form, and then found the solutions after setting up what are my basic variables, what are the free variables, and writing every variable in terms of the free variables. If you've done that correctly to this point, you'll pretty much have your basis. It's this set here with the vector negative 53, 9, and 1 in it. Right? So the set with this vector, negative 53, 9, 1, right, it spans the space clearly. Right, it spans the null space of A. Check. And is linearly independent because it's a single vector, right? It's a single non-zero vector. So it's definitely a linearly independent set. Check. So this set here is a basis for the null space of A. Right, that one vector is like the only building block you need to create this null space, right? Every vector in it is just some multiple of this, and it's clearly independent because, it's on its own. It's a single non-zero vector. Okay. Now, again, I say a basis, right? Bases are not unique. You've probably heard me say that several times in past videos, and if you've been watching. Because really, any vector that's a multiple of this, that's not zero, that's not the zero vector, would also be a basis. But this is like what I got from working through the problem. Wonderful. All right, and again, it should be that simple. Once, if you find the null space the way I have here, you should have a basis on your hands pretty readily. Okay. So the same for the rest of these problems. All right, this one's a simpler one, I think. So matrix A here is the matrix 1, 4, 2. This is a 1 row by 3 column matrix. So when we're looking at this equation, A times X equals the 0 vector, the vector X here is going to have to be a 3 by 1, right? The A is 1 by 3, so X needs to have three rows, right? So just like the first example, it's going to be a column vector with 3 components, x1, x2, x3. And then this 0 vector would just be the 1 by 1 matrix, right, with the number 0 in it, right? Because a 1 by 3 times a 3 by 1 would be a 1 by 1. Okay. So as I was doing before, when you multiply these two together and have it equal, when you look at this matrix equation, it corresponds to, this system. And there's only one equation here where you'd have, if I multiplied this matrix by this matrix here, this column vector, you'd have a single entry, a single component of the matrix. So 1x1 plus 4x2 plus 2x3. And in order for this statement to be true, that would have to be equal to 0. And this is it. This is your system of equations, right? There's only one linear equation. And the corresponding augmented matrix, you got the 1 row matrix here where coefficients of x1, coefficients of x2, coefficients of x3, little bar, and then zeros on the other side. Again, after this first couple examples, I will stop doing this and really only just focus on matrix A, right? Because that's all this side of the bar is matrix A. All right, 1, 4, 2 there, 1, 4, 2. And then I do row operations to put this in reduced echelon form, which it already is. All right, that's why I said this one's probably a little simpler. But this is already in that reduced row echelon form, right? The first non-zero entry, this pivot position here is a 1, and there's zeros above and below it because there's nothing above and below it, right? And that's it. So the only basic variable is x1. Right, this is the first column here. x1 is basic. Okay, so then the other two columns are not pivot columns. They don't have the leading 1 in it. So x2 and x3 are both free variables. I can replace them with any numbers I wish. Now, like I said, I like to do this myself, right? You can leave it as x2 and x3 if you want. I'm going to replace x2 with some parameter s, and replace x3 with some other parameter, right? T, right? Just again, just expressions that represent any real number. Right, so I could replace s with 15 and t with -5 or whatever, right? Infinitely many possibilities. All right, then looking at this here, sorry, lots of arrows, I know. This is telling me that x1 plus 4x2, so plus 4s, plus 2x3, so plus 2t, must be equal to 0. Right? And solving this, getting all my I want to get every variable in terms of these free variables s and t. Solve this for x1. x1 would be -4s minus 2t. All right. So now I have every variable, right? x1, x2, and x3 in terms of these free variables, s and t, these free variable, these parameters. So I describe the solutions, right? The solutions of this ax equals 0 equation all look like this. So every vector x, I can replace that with, right, look like, you have x1, x2, and x3. Each one of them takes these forms. x1 is, again, -4 times whatever I choose for s, -2 times whatever I choose for t. x2 is s, x3 is t. Alright, and then now this time there are two free variables, s and t. So I'm going to split up this vector into the sum of two vectors, one involving each of my free variables. And if there were 3 free variables for some reason, I'd split it up into the sum of 3 vectors, and so on. So you see how I'll split it up into the terms involving s. So you have -4s in that first component, s in the second component, and then no s, so 0 in the third component, and then plus, and then all the terms involving t in each of the components. You have -2t, no t in the second component, so 0, and then t in the third component. And then each of these, kind of like the last example, I can pull out scalars from vectors, right, using typical scalar multiplication definition. So I can pull out s from this one and t from that one. So we're getting s times the vector -4, 1, 0, plus t times, sorry about the clutter here, the vector -2, 0, 1. All right, so what we're seeing, and I'll just say this out loud, all right, what we are seeing in this line here is that every solution of this equation, this ax equals 0 equation, every solution of it is just a linear combination of the vectors -4, 1, 0 and -2, 0, 1. All right. So you could write that out as a description when you talk about the null space of A, but I'm just going to write it this time just as a span. All right. So the null space of A is the span of these two vectors, -4, 1, 0 and -2, 0, 1. Okay, so I got that much. All right, just a set of all linear combinations of these two. And this set of vectors, the set with -4, 1, 0 and -2, 0, 1. Okay, this set of vectors would be a basis for the null space of A, right? Because they obviously span the null space, I'll just do this. Just one more. Again, just one more example, and then we'll do some shortcuts. Just write the ending for future examples. So that this set definitely spans the null space of A, right? Because every vector in it can be written as a linear combination of these two, and they'd be linearly independent, right? If you do the reduced row echelon form correctly, and the way I've been working these will be independent vectors, and you can double check. There's only two of them this time. And remember, a set of two vectors is linearly independent if they aren't scalar multiples of one another. Well, I mean, you can take -410. You can't multiply this by any scalars to get -201. You can try it all day long. You'll never find it. So these are I'll just write independent, right? Linearly independent. Right. So check on both of those. So that means that this set with these two vectors is a basis for the null space of A. All right, these are some building blocks. Every vector in the null space of A, right, or just every solution to that AX equals 0 is a linear combination of these two. And these two are both necessary to be able to build every vector in the null space of A. They're independent. You can't just say, oh, because one of them, none of them depend on each other, you can't just get rid of them. Right? You have to have both. All right. So now in the next examples, I'm just going to set up, we're just going to focus on to find the null space, putting matrix A in reduced echelon form, or reduced row echelon form. All right, so here, matrix A, this is a 3 by 3. All right, 3 row, 3 column. So again, when I look at that equation that I'm trying to solve, AX, to find the null space of matrix AX equals 0 here, matrix A is a 3 by 3. So yet again, right, this isn't always the case. Right, this isn't always the case. You're going to see in a couple examples coming up. But so far in all my examples, the vector x, the solutions I were trying to find had 3 components. They were 3 by 1 matrices. And that's the same case here. All right. And, so 3 by 3 times a 3 by 1. And this 0 vector is the 3 by 1 0 vector, right, from R3. Okay, so like I said, I could do the whole thing where I set up the system and write the augmented matrix and all that, but this time I'm not doing that because everything has the same setup. All right, I'm just going to take matrix A here and just imagine there are zeros on the other side, right, with the augmented matrix. Right, I am not going to write these anymore, but just imagine they're there. I have blah blah blah, 3x1 minus 6x2 plus 21x3 equals 0. Negative 2x1 plus 4x2 minus 14x3 equals 0. And then x1 minus 2x2 plus 7x3 equals 0. Imagine the equal zeros on all these when I'm solving this equation here. All right. So I'm going to put this in reduced echelon form, or reduced row echelon form. Now this time I'm going to go to the calculator. If it would turn on. There we go. All right, so then you go to the matrix menu, right? I'm going to go over to edit. Matrix A, like I like to do, and this is a 3 by 3 matrix I'm reducing, right? First row, 3, negative 6, 21. Second row, negative 2, 4, and negative 14. And the third row, 1, negative 2, and 7. Alright, then get out of here, go to the quit, and back to the matrix menu, over to math, I'll put reduced row echelon form, RREF, right? Not REF, that's regular echelon form, or that's row echelon form, which is sometimes just called plain old echelon form. We want reduced row echelon form, RREF, right? And then the matrix A under names. Okay, so look at this, right? A couple rows of zeros here when I'm done with this. All right, so we got 1, 0, 0, then negative 2, 0, 0, then 7, 0, 0. And again, imagine there's the equal zeros on the other side. So you'd be fine, in solving the system. You'd have 0 equals 0, 0 equals 0. Those are true statements, right? The only one that really matters is this first row with the non-zero entries. All right, so I'm looking for pivot positions, pivot columns, right? First row has one of these leading ones, and not the first non-zero entry is a 1. So this pivot position here is in the first column, so x1, right, of the x1, x2, x3. x1 is basic, and that's the only basic variable. Looks like because the other two do not have one of these leading ones in it. The other two columns do not have a pivot position. So x2 and x3 are both, again, free variables. All right. As I've been doing with the free variables, I'm going to replace those with some other parameters, other expressions. So I'm going to replace x2 again with s, and x3 again with t, where s and t are just any real number I want, right? These can be anything I want, right? These are the free variables, s and t. And once I replace these with anything I want, right, then x1 can be found, right? You can't just replace all three of them with anything you want. All right, and then from the first row, again, remember, there's an equal 0 here. I just didn't write it. We have x1 minus 2x2, so minus 2s, and then plus 7x3, so plus 7t is equal to 0. And I solve for, I want to make sure I get all my variables, x1, x2, x3, in terms of these free variables, s and t, that I called them. Right? So this would be 2s minus 7t when I solve for x1. Great, so now every single variable in the problem here, x1 through x3, is in terms of these free variables, these parameters, s and t. So the solutions, every solution, every vector x that I can replace up here to make this equation true, looks like this. Now, I'm not going to write the x1, x2, x3 this time. I'm just going to write what they look like. 2s minus 7t, then x2 is s, x3 is t. All right, and then just like the last problem, two free variables, s and t. So I can split this this description of the solutions up into the sum of two vectors, one involving s, one involving t, and then pull those scalars s and t out. So if I have the one with the s, I pull the s out, and then times the vector, and then just go down the coefficients of s. First component has 2s, second component is 1s, then no s. All right. And then plus, and then the coefficients of t. T times, and then the vector, go down through. There's negative 7 in the first one, 0t in the second one, 1t in the third one. Okay. And then now we basically have our null space. Okay, so the null space then of A is the span of these two vectors. Right, so the null space of A is, you can write this out and say s and t need to be real. And it's all linear combinations of 2, 1, 0 and negative 7, 0, 1, or again the span of the set with these two vectors. Right? So again, got that. That's the first part with the null space of A. And then the basis is, again, the set with just these two. Alright, if you're doing everything correctly, those should form a basis. The set with just the 2, 1, 0, and the vector negative 7, 0, 1. Again, obviously it spans the space, right? It spans the null space by definition of span. Right? And again, we have two vectors here that are not scalar multiples, so they're linearly independent. And again, they should be if you did everything correctly in the reduced echelon form. So this is a basis for the null space of A. Alright. Alright, I've got two more here. Next one. Got this is a 3 by 2 matrix. Okay, so 3 rows, 2 columns. So again, when I look at the equation we're trying to find solutions for when finding the null space, A times x equals 0 here. The vector x, right, this column vector, needs to be a 2 by 1, right? This is a 3 by 2. This needs to be a 2 by 1. So vector x is going to be from R2, right? I have a column vector with 2 components, so just x1, x2 this time. So the null space this time will be a subspace of R2 instead of R3 like the past several examples. Okay, and then just as before, imagine, right? Again, you can just put this in here, put the matrix A in there, set up the system of equations and the corresponding augmented matrix. Well, you can just imagine there's and again, if you multiply these two, 3 by 2 times a 2 by 1, you're going to get the 3 by 1 0 matrix. So you have these 3 zeros over here, 3, 0, 0, 0. Just imagine they're there, right? Equals 0, equals 0, equals 0. And I'm going to put this matrix into reduced echelon form, or reduced row echelon form. Alright, now this one's not so bad. I can actually do this out loud pretty quickly. Because look, if you take that first row, multiply it by 3, you'll have negative 48. Add it to the second row, that'll make that 0. And then 3 plus negative 3, that'll make a 0 row. And then do the same thing, multiply the first row by negative 5. And that'll be positive 80, then plus the negative 80 will be 0, and then negative 5 plus 5 will be 0. So the last two rows will be 0 rows. And then to get the first row to have a pivot of 1, right, instead of negative 16, I would multiply by negative 1/16. Alright, so in reduced echelon form, the matrix is this: 1, then negative 1/16, then a couple rows of zeros, right? Because again, these bottom two rows are just a multiple of the top row. Right? Again, don't forget the equals 0 over here. Alright, now determining which variables are basic and free. Again, just looking for those pivots. First row has a leading 1, right? This non-zero 1 here. Pivot. So the first column's a pivot column. So of the x1 and x2, x1 is basic. And the second column is not a pivot column, doesn't have one of these leading ones in it. So x2 is free. Alright, now as I like doing, I'm going to replace x2 with an expression that can be any real number. Now you've seen me do in again past videos something like this before when there were fractions involved, like I have here, negative 1/16. I could replace x2 with just t, like I usually like, but just because there's this fraction coefficient of x2 here with a 16 in the denominator, I'm going to replace x2 with some expression that'll get rid of that. I'm going to replace x2 with 16t. And the reason for that is when I take negative 1/16 times x2, that will be negative 1/16 times 16t. The 16s will cancel, I'll have just negative t. Right, that is the reason I'm doing this with, and again, t is any real number. Right, and 16 times t can be any real number you wish, right? Just replace t with the appropriate value and you can have that expression represent any real number you want. Okay, so then from this first row, I'm seeing that x1, then minus 1/16 times x2, so 1/16 times 16t, so that's just minus t. Again, the whole reason I did the replacing x2 with 16t will be equal to 0. And solving for x1 in terms of the free variable t, this parameter t, x1 would be equal to t. Right. So now all my variables x1 and x2 are in terms of this free variable t. Right. So the solutions to this ax equals 0 then look like this. X1, the vector x is this two-component vector where x1 is whatever value of t I choose, and x2 is 16 times whatever value of t I choose. And both of these, there's only one free variable, so I've only got see the one vector here with all the free variables in it. Each of them, I'll pull that scalar of t out, that real number t out, and then I have t times the vector 1/16. Right. Okay, so we're seeing here that the null space of A is equal to the span of just the vector 1/16. Alright, so all this is saying is that any scalar multiple of the vector 1/16 will be a solution to this equation. You can try it out on your own. Just replace t with any number you want. 1/2, 3/4, -5, 1,000,000, and then multiply by 1/16 here. Plug it in, multiply by matrix A, and you'll get the 0 vector back. I promise you. Alright, because I feel like I did everything correctly. I know I did. And then this set with just the single vector is a basis. Alright. And the set with just the vector 1/16 in it, that's the building, a nice building block for this null space, right? This is a basis for the null space of A. That as well. Great. Wonderful. All right. So now, so far, every example, the null space has had infinitely many vectors in it, right? Every example I've shown so far, the equation ax equals 0 has had infinitely many solutions, right? There have been free variables, and maybe you noticed also that the number of free variables corresponded to the number of vectors in a basis, right? There was one free variable, this t, in this example, and there's only one vector in the basis there. In the last example, there were two free variables, s and t, and there were two vectors in a basis. Right? So you'll see for these null space problems, the number of free variables corresponds to the number of vectors in a basis for the null space. All right. Well, what if what if this equation didn't have infinitely many solutions? It's always going to have one, though, right? It's always going to have at least that trivial solution when the x vector here is 0, is the 0 vector. It's always going to have that. That's always making this true. And if that's not the only one, then you have infinitely many like we've seen. But what if that is the only one? All right, we'll see that here. So I've got one final example. All right, so this is a 2 by 2 matrix with the entries 1, 2, 4, -3. And again, if we're looking at this equation, a times x, when's this equal to the 0 vector? This is a 2 by 2 matrix, so it's got two rows, 2 columns. The vector x then would have to have 2 rows. So again, x is from R2, right? This column vector with components, x1 and x2, let's say. Right. And this would be equal to the 2 by 1 0 vector on the other side. All right. So again, remember, just imagine I set up the system of equations, the corresponding augmented matrix with some zeros on the other side here. Just imagine that that's there, the equals 0 equals 0. And I put this in reduced echelon form, or reduced row echelon form. And no need for a calculator here, because this one I know the determinant's not 0, right? It'd be a -3 minus 8, so -11. The determinant's not 0, so this has an inverse, meaning when I put it in reduced echelon form, this square matrix, it's going to be the identity matrix. 1 0 0 1. And again, you could also go through the operations. Take -4 of this row and then add it to this row to make a new row 2. And then you'd have something here and make that into a 1, and then eliminate the one above it, right? You'd see that you could make this into the identity matrix in reduced echelon form. And look at the pivots. Lead 1 there, lead 1 there in the rows. So there's a pivot in the first column, pivot in the second column. X1 and X2 are both basic. You can't just let X1 and X2 be any value you want. In fact, looking at the rows, the value of x1 must be 0, and the second row here, the value of x2 must be 0. Again, I'm imagining the equals 0 over here. So the only solution to this equation, this ax equals 0 equation, so the only solution is the 0 vector, where the vector x here is the vector 0 0. Alright, so that makes up the null space. So now instead of the null space having infinitely many vectors in it, here's a matrix where the null space of this matrix is just the set with the 0 vector in it. Okay. That's it. That's the only solution to that equation. Alright, now for a basis. You got to be careful with this. All right, I think I mentioned this in it's been a while, but a video in the past. Again, if you've been watching, paying attention, you might think, oh, well, remember this is not. I mean, I guess you could also say this was the span of this vector, because any scalar multiple of 0 0 is still 0 0. But I'm just going to write just the vectors. It's only got the vector 0 0 in it. And you might think, I'm going to ask this question: is the set with just the 0 vector in it, is the 0 vector, does that make up a basis for the null space? I mean, it clearly spans it, right? Every vector in here, right? Only this one vector is a scalar multiple of this, right? So I've got that. So I've got it spans the null space. Sorry, I got a faint marker here. Let's get rid of that. Alright, so it spans the null space, fine. But is it linearly independent or dependent? If I were to take a multiple of this and set it equal to the 0 vector, would it only have the trivial solution, right? If I were to take say x1 times 0 0, and say, when is that equal to the 0 vector, 0 0? Is x1 equals 0 the only solution? The answer is no. Right, you could replace x1 with anything, 2, 3, 5, and it would still give me the 0 vector. So this set is linearly dependent, not independent. All right, so that's bad. So the answer to this question is no. Right? So against your better judgment, you might think this must be the basis for this set, but it isn't. In fact, because this set of the vector, just 0, 0, is linearly dependent, this vector space, the vector space with only the 0 vector in it, has no basis, has an empty basis, is what they say. So the basis for the null space of A in this case is empty. Right, you can write the empty set, just a set of brackets with nothing in it, or that circle with a slash through it. Remember, this is the empty set. Has no vectors in it. Alright. And if you think back to dimension, I've talked about dimension before. The dimension of a vector space is the number of vectors in a basis. Remember, the dimension of that vector space with only the 0 vector in it is 0, right? It has a basis with 0 elements in it, 0 vectors in it. So a little tricky, that one, right? When you come across the trivial vector space, right? The vector space with only the 0 vector in it. All right. So lots of stuff there. All right. How to find the null space of a matrix. Hopefully pretty simple, right? I mean, again, I'll just describe the shortcut one more time. I want to find the null space of a matrix. Put that matrix in reduced echelon form. What are my basic variables? What are my free variables? And again, you're imagining the equals 0 on the other side of some augmented matrix. And then you just, set up every variable, solve for every variable, get every variable in terms of the free variables, and describe all the solutions. And there's your null space. And then if you've done that correctly, then the set that spans the null space should be a minimal spanning set, right? So it should be a basis for the null space as well. Great. All right, so I hope you have a good time practicing stuff like this, and thanks for watching.